Welcome to Chapter 6, Electronic Structure of Atoms. So what happens when one turns on a neon light, like some of these that are used to illuminate this cave? Well, the electrons in neon atoms, excited to a higher energy level by electricity, emit light when they drop back to a lower energy. The pleasing glow that results is explained by one of the most revolutionary discoveries of the 20th century, namely something called quantum theory. This theory explains much of the behavior of electrons in atoms, and we will see that the behavior of subatomic electrons is quite unlike anything we see in our macroscopic world. In this chapter, Chapter 6, we'll explore quantum theory and its importance in chemistry. We'll begin by looking more closely at the nature of light and how our description of light was changed by the quantum theory. We'll explore some of the tools used in quantum mechanics, the so-called new physics that had to be developed to describe atoms correctly. We'll then use the quantum theory to describe the arrangement of electrons in atoms, or what we call the electronic structure of atoms. So first, before we can know a little bit about the electron, we need to know a little bit more about waves, and therefore the wave nature of electromagnetic radiation. First of all, waves have something called a wavelength, symbolized by the Greek letter lambda. The distance between corresponding points on adjacent waves is called the wavelength. Get used to that Greek letter lambda and know that it always means wavelength. The number of waves that pass a given point per unit time is called the frequency, and it's symbolized by this little symbol right here that looks like a V. It's actually another Greek letter, but it looks kind of like a V and it stands for frequency. For waves traveling at the same velocity, the longer the wavelength, the smaller the frequency. And therefore you can see that wavelength and frequency are inversely proportional to one another. In other words, if one gets bigger, the other one gets smaller. If one other wave frequency gets bigger, wavelength gets smaller, as long as they're traveling at the same velocity. Well, electromagnetic radiation is a form of wave energy, and all electromagnetic radiation travels at the same velocity, travels at the speed of light. Now, because electromagnetic radiation carries energy through space, it is also known as radiant energy, and there are many types of this radiation in addition to visible light. You can see right here there's a small portion right here that is actually called the visible region. Red, orange, yellow, green, blue, indigo, and violet. The rainbow of colors that we normally see. These different forms, like radio waves, carry music to our radios and to our ears. Infrared radiation is heat radiation right here that comes like from a fireplace. X-rays are used by a dentist to obviously X-ray our teeth. All these may seem very different from one another, but they all share a certain fundamental characteristic. One is that they all travel in the form of waves. Two is that they all travel at what's called the speed of light, symbolized by the letter C, which is 3 × 10⁸ meters per second. And therefore we can say that C, the speed of light, is equal to the wavelength times the frequency for any type of electromagnetic radiation, whether it be radio waves, infrared waves, ultraviolet rays, gamma rays. It doesn't matter. They all travel at that same speed. The wave nature of light does not explain everything, though. And in the late 1800s, there were three particular phenomena that could not be explained by this model. And 3 that are particularly important to our understanding of how electromagnetic radiation and atoms interact are the emission of light from hot objects, This is known as black body radiation because the objects study appear black before you heat them up. The second one that was kind of unknown at the turn of the century was the emission of electrons from metal surfaces on which light shines, which is known as the photoelectric effect. And the third one was the emission of light from electronically excited gas atoms, like we talked about with neon lights at the beginning, known as an emission spectra. We'll examine each one of these phenomena here. Max Planck explained black body radiation by assuming that energy comes in packets called quanta. And Einstein used this quanta assumption to explain what is known as the photoelectric effect. And if we take a quick look, we can see a couple of other pictures of these phenomena. First of all, before we look at the phenomenon, let's look at another picture of the electromagnetic spectrum. You can see here that the frequencies increase from red to yellow to blue to violet in the visible range. And then there are also other frequencies that we can't see that would include things like X-rays and gamma rays. And you can see that the wavelength is inversely proportional to that. The wavelength gets shorter, and you can see shorter wavelengths right here in the gamma ray region, and longer down here in the microwave, infrared, or radio wave region. And you can see that the frequencies there are smaller in the microwave radio wave region, whereas the wavelengths get bigger compared to X-rays and gamma rays. The photoelectric effect said that when you shine a light or a form of electromagnetic radiation onto a surface, the surface will eject electrons. And they could tell this because the movement of electrons was actually the flow of electrical current. And so they could measure that, hey, there's some electricity flowing here, so we can make electricity flow just by shining light on a various metal. Well, it depended on what light you shone on the metal. Red light, for example, on potassium wouldn't eject any electrons, whereas green or blue light would eject electrons. Why did only green and blue light eject electrons and cause the photoelectric effect, whereas red light could not? Well, Einstein explained this in terms of quanta of energy using Max Planck's idea. And he concluded that energy was proportional to frequency. If energy is proportional to frequency, he said E is equal to h times the frequency, where h is a constant called Planck's constant. And since h is a constant, E was directly proportional to the frequency. Therefore, the higher the frequency of radiation, the more energy that radiation possessed. And if we look back here, at our pictures, who has a higher frequency? Red visible light, green visible light, or blue visible light? And you can see that frequency increases from left to right, and therefore red is the lowest energy light, green's a little bit more energy, and blue's even a little bit more energy after that. And therefore that's why red light shown on this surface did not have enough energy to emit electrons, whereas green and blue did. And therefore the photoelectric effect depended on the frequency of the light or of the radiation that's shown on it. Therefore, if one knows the wavelength of light, one can calculate the energy in one photon or packet of that light by using these two equations. First of all, we can use the C equals lambda times frequency equation, wavelength times frequency. And secondly, we can use the equation energy is equal to Planck's constant times the frequency. And knowing that frequency and energy are directly related, the higher the frequency, the higher the energy. Well, the third mystery that we said we were going to look at, called emission spectra, came from the observation of energy emitted by atoms and molecules when they were given energy, usually in the form of electricity, but also in the form of heat. Well, normally when you take sunlight and you put it through a slit in a prism, you get a rainbow of colors. You get red, orange, green, blue, yellow, indigo, and violet. Not in that order. But you can see right here that you get a rainbow of colors because white light is the composition of all the colors. And so you'd think that if you heated up a gas and made it so it would glow, it would have all the colors in it as well. But the problem is, when you heat up certain substances, they only give you a line spectrum, or discrete wavelengths of light that are observed. Here are two examples. Notice sodium only gives you a yellow shining of light. And as a matter of fact, when we did this demonstration in class, when we put a sodium salt into a flame and burned it, it gave only a yellow color. Hydrogen, on the other hand, when you heat it up, gives you a red, a blue, and a couple of purple lines. And if we look here, here is a photo of several different substances' emission spectrum. At the top here is sunlight. You can see you get red, orange, yellow, green, blue, indigo, and violet. Whereas hydrogen just gives you red, blue, and a couple purples. Helium gives you red, yellow, a few blues, and a purple. Mercury gives you a few more, a couple oranges, a couple of yellow greenies, and a couple more. And then uranium gives you lots of different colors as well. But notice that there's a lot of different things missing. And this turned out to be unique to each substance. When it was energized, it would only give off various frequencies of radiation. Well, we'll come back to this slide in just a second. Scientists couldn't explain this without using Max Planck's idea of the quantization of energy. And Niels Bohr adopted Planck's assumption. Niels Bohr was another famous scientist around the turn of the 1900s. And he used Planck's assumptions of quantized energy to explain the phenomenon in this way. He said that electrons in an atom can only occupy certain orbits corresponding to certain energies. And because of this, electrons in permitted orbits have specific allowed energies, and these energies will not be radiated from the atom. Energy is only absorbed or emitted in such a way as to move an electron from one allowed energy state to another, and the energy is defined by E equals h times frequency. These allowed energy states were furthermore used to calculate the energy absorbed or emitted using an equation called the Rydberg equation, where the change in energy due to a movement of an electron from one allowed energy level to another was equal to the Rydberg constant times 1 over the final position of the electron minus 1 over the initial position of the electron. Notice they're squared as well. These positions of the electrons are called allowed energy levels. And they try to put those on this little diagram over here where they say this is the first allowed energy level, the second, the third, the fourth, the fifth, the sixth, and then this would be infinitely far away from the nucleus of the atom. Well, another way to take a look at this if you look at this picture, is to say, here's the nucleus of an atom. These lines right here represents, and this isn't completely right, but close to right, possible places where the electrons can be. And they're only allowed to be somewhere in these so-called orbits around the nucleus. When the electrons move from a higher orbital to a lower orbital, they release energy in the form of light. And depending on how many levels these electrons move, different types of light will be released, light or electromagnetic energy, whether it be red or yellow or green or blue, dependent on how far the electrons moved. How far the electrons moved. In neon, of course, you can get various different colors depending on which way or where the electrons move when electricity runs through that gas. Well, Louis de Broglie, another famous scientist, came along a little bit after Einstein and Planck and Niels Bohr, and said, well, since you're treating these electrons a lot like light energy, and you're treating them like waves, how come everything else doesn't act as a wave as well? And he actually said, everything else does act as a wave, you just might not be able to see it. And so he said, a soccer ball acts like a wave, not as a particle. He said that a softball acts like a wave, not as a particle. He said a bullet acts like a wave and sort of like a particle as well. And Louis de Broglie postulated that if light can have wave-like properties, matter should be able to exhibit these as well. And he came up with this equation right here, that wavelength is equal to Planck's constant divided by the mass times the velocity of the object. And he demonstrated that the relationship between mass and wavelength was this famous equation called the de Broglie equation. It turns out that softballs, baseballs, bullets, they all act as waves. The problem is that you cannot see them acting as waves. They look just like particles to us because they're so large. When things get on the tiny, tiny scale, the nanoscopic scale, like electrons, then they start to act more like waves. Sure, they still act kind of like particles, but they also act like waves. And so sometimes I like to call them wavicles because they act as a particle and as a wave. Because of this, Werner Heisenberg, another famous scientist in the early 1900s, showed that since electrons act as waves and they act as particles, you can't treat them individually. You can't say it's a particle and I know exactly where it is and how fast it's going, because you will be uncertain of that due to its wave characteristics. If you treat it simply as a wave, you can't say you can't know its position for sure, but you could know more so its velocity. And Heisenberg showed that the momentum, which is the mass and the velocity or the speed of a particle, if that is known, the less precisely the precision is known of where its position is. Or conversely, if you know its position, you cannot know its momentum very well. In many cases, our uncertainty of the whereabouts of an electron is greater than the size of the atom itself. And so the uncertainty principle is important because it said, we're not really sure where the electron is, but we can probably tell you an area or a volume where it might be. And in our next few video casts, we'll look more precisely at the mathematics that describe where the electron probably is, and the result of these great pillars of physics in the early 1900s, and how they invented a new form of physics to describe this probability zone or probability map of where electrons most likely are, and the steps that allows us to take to describe the nature of matter.